Okay, let's get started. If you have a homework 1 to turn in, there's a growing pile up at the front for you to turn homework 1 in. Any questions? So I got several questions about homework 1 late in the evening last night. And you notice that I did, and for those of you who asked, I didn't respond. So just note that if you ask things at the 11th hour, I'm unlikely to be able to answer because I'm probably sleeping. Okay, so if I get an email like at 3 a.m., like I'm not going to get to it. I'm not awake 24 hours, even though you may think I am. But yeah, so just be mindful of that. So I'll try to grade these quickly. Probably get it back to you like Monday or something. Okay, so homework 2 is posted. It's due a week from today, and it should be not terribly easy, but easier than homework 1, I think. So the first question here is doing the Sperner family method that we talked about last time, which is the optimal construction where we picked every subset of a certain size from a set, and we just strung them all together. So basically it's just, do you understand the method? That's the basic idea. For the second question, it's getting more into research type questions, even though the question itself is easy, it's getting more into that insight. So the questions that we've been talking about with covering arrays are that every interaction appears once at least. But you may want to make a little diagnosis of, well, every interaction appears at least once. Well, how many appear more than once? Or how many appear twice? How many appear 3 times? How many appear 4 times? So if I wanted to have some kind of redundancy in my testing strategy, well, if I have an array where everything is covered once, well, it might be the case that only a small handful of them need to be covered again if I wanted to have everything be at least twice, for example. So this is just a simple diagnosis of, well, how many interactions have appear exactly once? How many appear exactly twice? How many appear exactly 3 times? And it's just trying to understand if I wanted to get to higher redundancy in my testing strategy, how many interactions do I need to consider then? So, and then from there, once you do question 1 and 2, you can answer questions about, well, I have, say, a certain number of rows for the case we're considering here. Well, what if I have 1 fewer column? What if I have 1 more column? What if I increase the number of symbols by 1? What if I increase the strength by 1? And we'll talk about bounds that you can get from that today, probably. So, and then the other questions are just project ideas, which I think are kind of interesting. Any questions on homework 2? Okay, so let's get back into covering array stuff. Sorry, I can't get that projector to work. We'll just have to rely on this. I might have to use the board if needed. Yeah, okay, so we talked about this Sperner family stuff last time. And the recipe, if you remember, is really, really simple. Just list all possible columns of, with exactly 3 ones in this case. Sometimes you see in the literature that these columns have weight 3. Sometimes you see that terminology. So weight 3 means the number of ones in the column is 3. Sometimes you see that. Okay, so let's summarize where we are. So, okay, never mind. So, what we have seen so far is, if you think about how the method works, if you have a number of columns between these 2 binomial coefficients, then the optimal number of rows is n. And where do these numbers come from? These are basically just choosing all binary vectors of weight n minus 1 over 2. So remember, that we had the number of ones that we picked was the smallest number above half. So in the case that we talked about, we had 5 rows, the 5 black rows here, and we picked the smallest integer that's strictly more than half, which was 3. So that's actually where that comes from. So you see that there's a ceiling right there, where it says n minus 1 over 2 ceiling. That's getting to the integer strictly more than half. So if you have a number of columns between those two, then n is the optimal number of rows. But it turns out that only in this very special case do we know the recipe for the optimal number of rows for all numbers of columns. Yeah, so it's been actually of great interest, even if, say, for example, strength 2 and 3 symbols, we don't know the answer. Yeah, so that would be a really tough thing to be able to determine it for any other sets of parameters. A project idea I thought of when I was making these slides is we do know the answer for specific numbers of columns. So if I have the situation can of 2, 10, 3, well, it doesn't fit into 2 for the strength 2 symbols. It's strength 2 and 3 symbols, but nevertheless, we know what the exact answer is. So a project idea might be, what are these sporadic other cases that happen to that we happen to know the best value for? Because it involves understanding what the techniques were to find them. Was it just pure computation, or is it a case analysis, or something else? Yeah, so just going through those might be interesting. If you are interested in that project, you may want to look up the term orthogonal array. In the syllabus for the schedule, I said we're going to talk about orthogonal arrays today, but we're not going to be able to get to that. So I thought it might be better to just have that become a project. So if you're interested in that particular project, orthogonal array is a thing that you should search for. I do have this question as one of the project ideas too, which is for this specific case, for these specific parameters, what is the best known? And no one knows the answer. And if you're able to determine this question right here, can 2, 5, 10, you will become internationally famous overnight. And I'm not kidding. And you may think, okay, well, it's just professors who are who will say congrats to you in an email, that kind of international famous, right? So the last time that a question like this was resolved that was very similar to this, it was, I think, in the early 90s. It got to the front page of the New York Times. So the headline story was, mathematicians resolved this answer. So if you can solve that, you'll become internationally famous. But yeah, so that would be a fun project too. Because it's difficult and there are a lot of techniques you can use for them. Okay, let's move on to new topics. So you may think, okay, well, if I have an array right here, so I have, let's just say, n rows and k columns. And then you may be thinking, okay, well, let's just say I have some algorithm to make this thing. Is that the only way that we can make it? Or are there other ways that we could have made this array? Yeah, so is there exactly one way to make it, or are there multiple ways we can make it? And it turns out that there are many other ways we can make it. So let's look at a covering array, for example. If I take an array and I swap 2 rows, so the rows were like this, one was on the top, one was on the bottom, and we switch the order, does that affect whether it's a covering array? No, because if an interaction appeared in the top row, it now appears in the bottom row. And if it appeared in the bottom row, it appears in the top row. So that doesn't actually change anything. So if we swap the order of the rows, that doesn't do anything. What about columns? So I have 2 columns here, and let's just say I swap the order. Does that change anything about whether that's a covering array or not? Yeah.
Potentially, because if you're swapping columns, then the columns are what I guess the interactions depend on. Then you might I guess like remove an interaction or add a new one, with both of which would change, I guess, or change or remove interactions.
Okay, let's actually try it. So let's go to an actual example of a covering array if we have one. Do we have one? We do not. So let's actually use the Sperner family method and make a covering array for ourselves. So let's make a new page. Add page. Okay. So let's just try to make a covering array with n rows where we're going to determine n in a second, strength 2, and let's just say 5 columns and 2 symbols. So let's see. Well, will 3 rows be sufficient? Or do I need more than 3 rows? Well, how many rows do I need at least, no matter what? Not 5. It's less. It's between 3 and 5. I know it's early. 4. 4 is in between. Why is it 4 is the absolute minimum? Yeah.
Is it because you're looking at you have 2 symbols to choose from, and the interactions are strength of 2, so
Yeah.
it would be
2 times 2.
2 times 2.
Yeah, so it's 2 squared, but yeah. So no matter what, it's at least 4 rows. So let's see, what can we get with 4 rows? So if I divide 4 by 2, what is the smallest number at least 2? That's strictly more than half of 4. So if we divide 4 by 2, we get 2. What is the integer strictly larger than that half? 3. So let's make all possible columns with 4 elements and 3 ones. So one way to do that is 0, 1, 1, 1, then 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1, 0. And can I get any more than that? With 3 ones in the columns. No, I can't. And the Sperner family method said that's the best you can do. Shoot. So how many rows do I really need here then? I can't get away with 4 rows. Well, let's try 5. So let's see. If I divide 5 by 2 and get the integer that's strictly more than half, what is that? 3. Yeah. Well, it's the same answer as this one. So what I'm going to do is I'm going to put zeros above. Well, this works because because I still have exactly 3 ones in every column, but now I need a column where I have 3 ones and I need a 1 up here, but I can choose any one that I want. Let's just say this one. I'm just picking one, and of course I could have more columns than this. It's just that this is just a particular example. Okay, so let's make I'm going to copy this array right here. So this guy is the copy. And what I'm going to do is I'm going to swap the second and the third column in the copy, just to see what happens. So I'm going to swap this guy and that guy. And it's really easy to do in Notability. Although that one's kind of slanted. Okay, yeah, so I made a swap here. So what would I have to verify if this is still a covering array or not? Yeah.
Question, is the first one covering array?
Mm-hmm. Yeah, I forgot. Remember that the Sperner family method, what is the last thing that you do? Straight zeros, yeah. Yeah, that was my mistake. Yeah, you need to add the row of all zeros. Yeah, thank you for pointing that out. Now it's a covering array, I claim. Okay, so what would I have to verify in the copy that it's still a covering array? Well, what does the covering array property say? Or what is required, at least?
The same interactions that appear in one row inside the original covering array have to appear in the copy.
And not even that. It's just that every interaction appears. That's all we need. Well, in these two columns, does that change? In the ones that I swapped, does it really matter in these two columns by themselves? No, because I just swapped the order. Well, if it was 0, 0 somewhere, it's 0, 0 again. If it was 1, 0 before, it's 1, 0, 1 now. If it was 0, 1 before, it's 1, 0 now. And if it was 1, 1 before, it was 1, 1 now. So it doesn't change anything in those two. Well, what about if we pick one of the two columns and one different one? Does that change anything? No, why? It's actually the exact same reason. If it was 0, 0 before, it's 0, 0 now. If it was 0, 1 before, if it was 0, 1 before, then it just depends on what was in the other column, but it must appear at some point anyway, because the interaction with, say, the third column, let's just say we were looking at the third and the fifth column before. If we were looking at the third and the fifth column before, well, it's the same thing as saying we're now looking at the second and the fifth column because we swapped the second and third one. Well, because it was a covering array before, every interaction with those two columns appears, so now it still appears. So because the property says every pair of columns has every interaction appear, if we just swap the order, that doesn't change anything. So that's just a short proof of why the order of the columns does not matter, because we look at every pair of columns, then no matter how I orient the columns, I still have every pair there because I don't change any of the columns. I just swap the order. So in fact, if we permute the columns, it doesn't do anything. Pretty cool. So any questions on that first one?
Yeah, so what if you had a row that was originally a bunch of ones and the second to last thing was 0 and the last thing in the row was 1, and then you swap those two columns, wouldn't you remove that 0, 1 interaction?
Yes, in that particular row, but it appears in some other row. Because okay, so let's look at your example. So you're saying that we have some array right here, and then we have a row of 0 with a bunch of 1s in it, I'm guessing?
Yeah, and then the second to last item is 0, and the last item is 1. Yeah.
So something like this.
Yeah.
Okay, then now what?
And then if you swap the last two, if you were to swap the last two columns, then it should be removing the 0 interaction. Just looking at 0.
Yeah, so okay, so I understand your question. So 0, 1, so this is the situation that we're going to have after that.
Yeah.
Okay, so let's see. So you're saying that the 0, 1 interaction appears in this row and doesn't appear in...
In the switch and the row.
Right,
switch
right.
to
It doesn't appear here anymore. Good. Well, the key here is that the original array was a covering array. Okay? So then in this before array, so let's just make it look like this. So look in those last two columns earlier up. Then because it was a covering array, 1, 0 has to appear somewhere else. So then 1, 0 appears somewhere else, but then when I swap them, then that same row above now has 0, 1. So, and you can think of it like every possible permutation of a particular interaction appears. So 1, 0 appears, and its permutation 0, 1 also appears. So every permutation will appear. So if I swap the order of the columns, it just changes the permutation. So it doesn't actually make a difference. Other questions? Okay. So let's look at this second one. So if we change the values within the columns, it yields another covering array. So this is actually kind of not so straightforward. So let's look at this, this one right here. I'm going to copy it. Let's paste it here. Maybe make it a little smaller. So here's what I'm going to do. I'm going to look at this fourth column right here. I could have chosen any one that I wanted. And what I'm going to do is I'm going to swap the zeros and the ones. So if it was a 0 before, it's going to become a 1 now. If it was a 1 before, it's going to be a 0 now. So I'm going to erase the column, and I'm going to swap the order. I think I got that right. So all I'm doing is I'm permuting the symbols within a single column. That's all I'm doing. So the array before was a covering array. Is the resulting one still a covering array? Yeah, why? There's always a question of why, right? Yeah.
The previous interactions were like covered by, if they were covered by 0, now they're covered by 1.
Right. So let's look at this. So if it was 0, 1 before in the column I'm changing and 1 somewhere else, well, now that same pair is going to be 1, 1. But if you look somewhere else, if we have a 1, 1 somewhere else, now it becomes 0, 1 because I swapped the order I swapped the values in the column. Would it be wrong of me to say that I'm going to change every value in the column to a 1? So instead of just swapping zeros and ones, I'm just going to change everything to a 1. Would that be wrong to do? Yeah. And in fact, in this case, look at the last two columns. There's no 0, 0 in there, or 0, 1 for that matter. So, so it's really important that you only permute the symbols. You don't just artificially fix one to another. You're just permuting the symbols. And a straightforward argument of why this works is if there was an interaction before and now it's changed to something else, well, that something else appeared somewhere before. Well, that changed to something even other else, to something completely different. But because you're doing a permutation, you will eventually find the original interaction that you were interested in. So in this case, that we have 0 maps to 1 and 1 maps to 0, but that just forms a cycle. 0 maps to 1, 1 maps to 0. So if you have an interaction involving a 0 before, and now it's a 1, you must be able to find another interaction that originally had 1 but now has 0 in it. So now every interaction still appears. Okay, we call these equivalent because if you do one of the transformations to another one, like flip 2 rows or 2 columns or whatever, you can always undo that change. So if I swap 2 columns, I can just swap them back. So they're equivalent. They're not the same, of course, because they're literally not the same, but they're equivalent. So here's an interesting point. We can assume that a covering array has a row of complete zeros. Or we can actually form an array that has all zeros in it for a row. Why can we do that?
I actually have a question.
Yeah.
So on the last example we just did,
Mm-hmm.
when you flipped the ones and zeros, you no longer had a row of all zeros.
That's fine.
That's fine.
Yeah. I'm not saying that every covering array will have a row of all zeros. I'm saying that we can make an equivalent one with all zeros. Yeah, so the array on the right definitely doesn't have a row of all zeros. That's definitely true. But it's just I can always form one that has a row of all zeros. Why can we do that? Yeah.
Because it's we're just using zeros and ones, then there's only 4 possible interactions. So presumably they would cover somewhere else. So you can,
But I could have more symbols, though. Well, think of the idea that we just did. Well, couldn't I just permute the symbols any way that I want? So here's what you can do. Just pick a row, any row that you want. Say this top one right here. If it's a 0 in that row, leave it. Don't change it. If it's not a 0, then permute the symbols in that column such that the entry in that row becomes 0, and whatever happens to the other entries, we don't care. So what we can do is, if it's a 0 in that row that we just picked arbitrarily, just leave it. If it's not, flip the symbols in the column until you have a 0 in that entry. And because we can flip the symbols in a column and not change the covering array in terms of equivalence, then we can have a row of all zeros. We can assume that there's a row of all zeros. So this process is called standardization. The reason why you would want to do this is so that, in fact, most algorithms that are used to actually make these things, they start off with a row of all zeros at the start. Well, then you may think, okay, well, can we always assume this? And it turns out yes. So you can actually speed up various algorithms by just making the row of all zeros and then continuing the algorithm from there, instead of having the algorithm make the row itself, because you always can assume that such a row is there. It is not true that we can always assume that we can have a row of all zeros and a row of all ones simultaneously. That's not always true, but sometimes it is true, sometimes it isn't. But we can always have one row of one symbol. That is always true. Any questions on that? Okay, I wanted to get to this slide before homework 1 was due, but it's obviously due. Because one of the optional questions had this. So this is actually a really important term because it is really useful for some algorithms to make the covering arrays smaller while still being covering arrays. So we have T be a T-way interaction, just some interaction. If T appears in a certain row and doesn't appear in any other row, then the in that particular row for those columns, we need to have those values fixed there. Yeah, so let's look at an example. So let's look at this, the array on the left here. Let's look at the first 2 columns. So is there a two-way interaction in those two columns that appears exactly once? There are actually quite a few. Oh yeah, 0, 1, and 1, 0. Does a 0, 1 appear anywhere else in these two columns? No. So these two entries then are necessary or fixed or something like that. They need to be those two values. They cannot be any other value. Because if I change one of them to say a 1, well, that just destroyed that interaction and it doesn't appear anywhere else. So we need to have those entries fixed to those values. And same story for the 1, 0 right here. For the 0, 0 and the 1, 1, that's not true anymore because they appear multiple times. Okay, so it may be the case that I can change one of them, say like this one right here. I might be able to change it. I don't know for sure. But the 0, 1 and the 1, 0 in these two columns, I definitely can't change. So those are necessary values. Okay. Any questions on what the meaning of that is? So necessary means that it participates in some interaction that appears exactly once. So like those 0, 1 and the 1, 0 in these two columns, they appear exactly once, so they must be fixed to those. If it doesn't participate in any interaction appearing exactly once, then it can change to any other value because it doesn't need to be fixed to a value. So we call them flexible entries. Or sometimes another term that we use here is don't cares, because we don't care what the value is. Okay, so this is kind of going for the solution to the third question on your homework. Let's look at this array right here. And let's try to identify if there are any flexible entries, if there are any don't cares. So what we're going to do here is I'm going to put a box around ones that I can say are definitely have to be fixed to those values. So I already did them for these two columns here. So those 4 values have to be fixed. They cannot be changed. Let's look at the first and third columns. So which ones have to be fixed? So the 0, 0, does it have to be fixed? No, so I'm not going to touch that. Well, what about the 0, 1? Well, the 0 at the beginning has to be fixed because we already determined that. What about the 1 after that? Does 0, 1 appear anywhere else in these two columns? No. So in fact, the 1 right here also has to be fixed. The 1, 1 appears multiple times. The 1, 0, does it appear anywhere else? In these two columns, the first and the third column? No. So in fact, these two entries need to be fixed as well. And then you would keep on going until you get to a point where you checked every pair of columns, and whatever remains, those can be changed to any value. Okay. Yeah, let's not do all of them. But that was kind of getting at what you were supposed to do for question 3, which is basically if you have a row, let's just say we did all the work right here. Let's say that we have a row, say that one, for example, although it's not in this case. We have a row of don't cares. They can be fixed to any value. What can we do with that row? We can remove it because there's no interaction that must be in that row because it appears somewhere else. So yeah, so that was what you were supposed to do for question 3. Any questions on what necessary, flexible, don't care, all that stuff means? Okay, so let's move on to some basic quote-unquote operations. So this is getting at what one of the questions is on your homework too. So I think the third question or something. So this is just asking looking at various bounds of the covering array number. So it's looking at various inequalities right here. So this is saying if I have a covering array with some strength t, some number of columns k, and some number of values v, then if I have one fewer column, then I may need the exact same number of rows or fewer. So the array number for k columns is at least as large as the one for k minus 1 columns. So why is that true? Think of this operation. Take an array and just strike out a column, delete a column. Is the resulting array still a covering array? In fact, it is. Why is it? So if I have a set of columns right here, and let's just say, I really don't like this column right here. I want to eliminate it. I just remove it. Well, what happens to what's the property of covering arrays that needs to be satisfied? Yeah, every interaction appears. Does every interaction appear among the remaining columns? Well, it did before, because when that column was there, if you look at any t-way interaction among any other set of columns, well, they appeared before. So if I took out that column, that doesn't change. So every t-way interaction still appears. So in fact, this is true. It may be the case that we can do fewer rows. But from k columns, we can derive k minus 1 columns. So the operation here is called truncation. We're truncating the array by striking out a column to get one fewer one. Okay, let's look at fusion. So this one is not as trivial as or straightforward as the other one. So this is saying, if I have an array with k columns, then if I want to look at, again, k columns, but one fewer symbol. So if I had 3 symbols before, now I have 2. This says that it's not only less than or equal to that value, but you can strike out a row as well. Well, why is that? So do I have an example? Yeah, so let's actually look at an example here. So I claim that this guy right here is a covering array of 9 rows with strength 2, 4 columns, so that's easy to check, and 3 values, which is easy to check, 0, 1, and 2. So what we're going to do is we're going to standardize on a row. What does standardize mean again? Make a row of all zeros. Does it have to be zeros? No, because I can permute the values in the column to get whatever value I want. So we're actually going to standardize the 2's. Okay, so in particular this last row. I could have picked any row, but let's just pick this last row. Well, the first entry is a 2. We don't need to do anything to it. The second entry is a 1. So what do we do here? Well, we got to permute the symbols in the second column so that I get a 2 at the bottom. Well, let's see. Well, all I'm doing here is I'm flip-flopping the 1s and the 2s and leaving the 0s unchanged, which is why I bolded them like this. So the 1 becomes a 2, 2 becomes a 1. So then, yeah, so I flip those. And then for the third column, I leave the 1s intact and I swap the order of the 0s and 2s. So a 0 becomes a 2, 2 becomes a 0. So then now I have a row of all 2's. What do I do? I'm trying to remove the 2's in this array. Well, let's see. Do I have a row of all 2's if I'm trying to remove all 2's?
No, you would want to do
But I'm only going to consider an array on 2 symbols now, the 0 and the 1. Well, do I have a row of all 2's? Yeah. Well, if I'm trying to make an array where every interaction has a 0 and a 1, no 2's at all, is this row of 2's completely unnecessary? Yeah. So in fact, I can strike out that row now. Because if I'm only looking at 0's and 1's now, the 2's are completely useless to me. So I can strike out that row. Well, what about the remaining 2's in there? Are they unnecessary? Yeah, they're completely unnecessary because every interaction only has a 0 or a 1 in it, in each of the 2 places. It doesn't have any 2's at all. So I can actually strike out every other 2 in this array because I'm only working now with 2 symbols instead of 3. So in fact, we can always remove a row because we can standardize on the removed value and then just strike out that row completely. Okay, so that is fusion. Yeah, so this is just a little summary. We standardized on the removed value, whatever you want it to be. Delete the row because now it's a row of 2's or whatever symbol it is. And change all remaining choices of that value to another. So the remaining 2's in our example down here, I can change to 0's or 1's, whatever I want. Okay, so if I happen to have 4 values, and I wanted to do fusion, I would just have a row of one of the symbols, and then remove it. Now I have an array on 3 symbols because I removed one of them. So let's talk about derivation then. So this is saying I have an array on some strength, some number of columns, some number of values, and now I want to look at the strength going down by 1 and the number of columns also going down by 1. But the same number of symbols. So, for example, if we were looking at can of, what would be a good example? 484. I just pulled those numbers out of my head. So then, if I wanted to instead look at can of 374, then whatever that value is less than or equal to 1/4 of whatever the 484 situation is. So there's a dependence now between various strengths. So if I wanted to know the optimal value of strength 2 of something, and I know the answer to strength 3, then I can just do this derivation step and I know the bound. And what do you do here? You choose some value that occurs least frequently and delete all rows where it appears. Yeah, is it least frequently? I think that should be most frequently. I'll have to think about that. I think this should be most frequently. I think that was my mistake. Yeah, it should be most frequently because we want to get the most number of rows removed. So I think I have an example here. Oh, maybe not. So here's what you can do. So let's actually copy. Okay, I don't have an example. So what I'll do is I'll quit class early today, and then we can pick up from here on Monday. So I'll see you then.